Question 5 is a binding energy equation, nuclear decay. So we need to find the mass defect first. So the defect in mass is the mass of all the individual particles that make the thing up, take away the mass of the thing when it's actually all bound together. So we've got 27 protons. So we need to times that by 1.6. Now when you're doing this, you must use the extra decimal place for the neutrons and the protons here. So that's 1.673 times 10 to the minus 27 plus the mass of the neutrons. There are 32 neutrons. 59 take away 27. 1.675 times 10 to the minus 27. And then we need to take away this 58.9330, and we need the mass of a U, which is there. So that's 1.661 times 10 to the minus 27. And then we're going to use E is equal to delta mc squared to find out what the energy is. So let's work this out first. Times by 1.673 27 plus 32 times by 1.675 exponent minus 27, take away 5, 8.93320 times by 1.661 times 10 to the minus 27. So that's the mass defect in kilograms. 8.8295548 times 10 to the minus 28 kilograms. So we need to do delta M times by 3.00 times 10 to the 8 all squared. So let's times that by 3 times 10 to the... So that is the binding energy in joules. 7.94653 joules, times 10 to the minus 11 joules, otherwise it would be very large indeed. Now we need to convert that to electron volts, and we need to write it in mega electron volts, which is equal to 496.66 mega electron volts. Right, we can easily write this to 3 significant figures. Everything's actually to 4 significant figures, so we can write it to 4 significant figures. I've done the whole calculation using kilograms. You can do the whole calculation in U instead, putting in the values of U here and then converting that into mega electron volts at the end. You actually get a slightly different answer here. Both are acceptable in the mark scheme, so that's fine. Now, I don't usually question Spot, but I noticed that there's no decay equation here using this, so, and there's no inverse square law, so they're quite likely to come up next time on a big question. Here we have an iron nucleus, which is decaying into one of these 3 metastable states of cobalt 59, and then these will decay down to the ground state by release of gamma rays. So calculate the maximum possible kinetic energy in MeV of a beta particle emitted here. So the maximum kinetic energy of the beta particle is this transmission from here to here, because that's the biggest energy drop there. We know that the total energy released from here all the way down to here is this much, so this energy here must be 2.52 times 10 to the minus 13 joules. So we just do the difference between that level there and that level there. Dead easy. So we've got 2.52, take away 1.67. equal to 0.76 times 10 to the minus 13 joules. So we've got this many joules, so 0.67 times 10 to the minus 13 joules, and we need to convert it to MeV, so we go divided by 1.6 times that to the, so that is equal to 475,000 EV, so that's 0.475 mega electron volts. Following the production of this, gamma rays of discrete wavelengths are emitted. State the maximum number of discrete wavelengths that could be emitted. Okay, this doesn't mean that they are necessarily emitted, but the maximum number is, you could go from that one straight down to there, you could go from that one straight down to there, and you could go from that one straight down to there. So that's 3. But you could also possibly go from that one to there, or that one to there, and you can also potentially go from that one to there. So that's a total of 6. That doesn't mean that in reality those 6 occur, just that that's the maximum possible number. So calculate the longest wavelength of emitted gamma rays, assuming that they all happen, I would hasten to add. So the longest wavelength is the lowest energy. The lowest energy is the shortest jump, which is, that's 0.3, and that is less than 0.3, so it's that jump there. So we need to have the energy is going to be 2.29 times 10 to the minus 13, take away 2.06 times 10 to the minus 13. So the energy of the photon is equal to 2.29, take away 2.06 times by 10 to the minus 13 is equal to 2.3 times 10 to the minus 14 joules. Then we need to use the equation E is equal to HF, which is the same as E is equal to H lambda over C, no, C over lambda, isn't it? C over lambda. So lambda is equal to HC divided by E. Planck's constant H there is 6.63 times 10 to the minus 34. Speed of light is 3.00 times 10 to the 8. And our energy is already in joules, so that's 2.3 times 10 to the minus 14. So let's put those in and see what happens. 6.63 10 to the minus 34 times by 3 times 10 to the 8 divided by answer. And we get 8.6478 times 10 to the minus 12. So that's 8.6. Let's have a look at decimal places. We've got 2 sig figs there, so we've got to do it to 2 sig figs. Times 10 to the minus 12, and that's 2 SF. State what's represented by gravitational field lines. So that's the direction of force. Objects with mass experience. In a field. Okay, so that shows you the direction. This one here suggests why the field lines are converging here onto this area. Well, field lines go into masses, so this must have more mass than the rest of the surface. So K must be denser. So K must be denser than J, perhaps containing heavy rocks, e.g. iron compounds. Okay, so this must be denser than this, that's the reason why. It says suggest, so that's why I've given a specific reason, but I don't think that was on the mark scheme. A ball travelling at constant speed passes J moving towards K. Right. I think they could have worded this question more clearly as to where the ball is. So I think the ball is rolling along the floor here. So if there's no friction, it's going to continue at a constant speed until it gets here, when there is a horizontal component of the field of gravitation, so it will be accelerated by gravity towards the right before it gets to K. As it goes past K, it will be decelerated by the exact same amount as it goes past, but we're only interested in towards K. So as it approaches K, it will accelerate because there is a horizontal component of the G field at K, oh, not at K, just before K. Acting right. Okay, this shows electric field. Explain why the lines of force cannot represent a gravitational field. Well, the lines always go into masses in a gravitational field, and these ones coming out. So lines always go into masses in a G field. L has lines going out. That's because a gravitational force is always attractive. Which has the greater charge, it's the one with the most lines. Which has a positive charge, it's the one with the lines coming out. Because remember, the lines show which direction a small positive charge would move, so that must be positive to repel them. Draw a line of equipotential passing through N. So lines of equipotential, the trick with them is to make sure they're always at 90 degrees to the field lines. So you get sort of that shape there. Slightly wonky. I think that would be a better line. It's more symmetrical, the whole thing's symmetrical, so the top should look similar to the bottom. Okay. Derive an expression to show that satellites in a circular orbit. This is true. Okay, so we just need to use the force due to gravity. So if we have a satellite, then the force on the satellite is due to gravity, so that's Gmm over r squared, where r is the distance from the middle of the satellite to the middle of the planet, or whatever it is, or the sun to the earth, whatever it is, and that's got to equal the centripetal force, which is m omega squared r. So that's the centripetal force, because that's the resultant force acting on it, and that will put it in circular motion, centripetal force there. So we can cancel the masses of the satellite, so that's irrelevant. Move that up there, and we get G times by big M is equal to omega squared times by r to the 3. Now, let's think about what omega is. Omega is equal to 2 pi f, which is equal to 2 pi over t. So omega is squared is equal to 4 pi squared over t squared. So we have Gm is equal to 4 pi squared over t squared r to the 3. So we move t squared up there, and we get t squared is equal to 4 pi squared r cubed. Bring those two down. And all of that is constant. So therefore t squared is proportional to r to the 3. Pluto is a dwarf planet. A mean radius of Pluto around the Sun is that compared with that of the Earth. Calculate its period. So it's a good ratios question, this. So if we have the time period of Pluto squared divided by the radius of Pluto cubed must equal the time period of the Earth squared divided by the radius of the Earth cubed. So we want to find out what Pluto's time period is, so we need Tp is going to equal Te squared times by Rp cubed over Re cubed. Well, we want it in years, so the time period of the Earth is 1. So that's 1 squared times by, if we just square root the whole thing, can't we? The radius of Pluto first, that's 5.91 times 10 to the 9 kilometers. So, but there's going to be kilometers on the top and kilometers on the bottom, so they're going to cancel each other out, so we don't need that. And that's going to be cubed divided by 1.50 times 10 to the 8 cubed. Okay, so we've got 5.91 times 10 to the 9 cubed, and we want to divide that by 1.5 times 10 to the 8 cubed. And we get that. We need to square root the whole lot. We get 247.3 years. Everything's to 3 significant figures, so that's 2, 4, 7 years to 3SF. This question here, notice its actual significant figures will get a mark for this one, even if you can't do the problem. But the problem is actually quite straightforward. We have that f is equal to ma, which is equal to gmm over r squared. Once again, my masses cancel. I can rearrange for the capital M, the mass of the big object, so in this case Pluto, and we get acceleration times by r squared divided by g. G is there, so that's just equal to 0.617 times by the radius, 1.19 times 10 to the 6, and that's got to be squared, divided by g, which is 6.67 times 10 to the minus 11. So this is just saying that the acceleration of the object is caused by the force due to gravity. So the force on the object is going to be going to cause its acceleration, and the acceleration there of a free-falling object is the same as g. So which is that on Pluto, and that should allow us to work out what m is. So we've got 0.617 times by 1.19 times 10 to the 6 all squared, divided by 6.67 times 10 to the minus 11 gives us 1.30994 ... times 10 to the 22, and we have 3 significant figures there, 3 significant figures there, so we can do the whole thing to 3SF, which is 1.31 times 10 to the 22, 3SF. So more on gravitational fields. We are seeing if an object that is fired with this velocity can escape. So all it needs is to have more kinetic energy than the potential from there to there. It's not from there to there, it's from there all the way to 0. That's escaping there. So we are going to do the kinetic energy of the object is going to equal a half mv squared, which is equal to a half times by m times by 1400 squared. So we have 1400 squared times by 0.5 gives us 9.80 times 10 to the 5 m joules. So the m is the mass of the object there, and the potential is equal to 7.4 times 10 to the 5 times by m to turn your potential into potential energy, joules. That is bigger than that, therefore it will escape, as long as it doesn't hit anything.